This talk, as you've heard, is on functional Swift. And it's basically an introduction into this kind of thinking and this kind of approach to building software. So I think it'll be interesting to those of you that are sort of new to the world of functional development, new to the world of Swift perhaps, and even veterans of both, or there's no veterans of Swift yet, but veterans of functional development. I think you'll find something to take away here as well. All right, so agenda tonight is really talk about myself for a second. Sort of the what is functional programming, why is it interesting and why is it sort of beneficial? Sort of the key aspects of the functional approach, a bit of a toolbox to take away in terms of using some of these functional techniques. Talk about Swift, value types versus reference types, which is kind of important to understand functional. And then app architecture and some of advanced stuff and next steps. Okay, so let's start off. Who am I? So, as you heard, my name is Farley Caesar. I've been programming since the early 80s, so probably a little older than I look, I hope. Basically graduated the comp sci from U of T, programming professionally since 97, so far back there. With Bell Sigma, IBM as well. I'm a solution architect right now at RBC, so I don't do a lot of coding in my day job, but that's going to change soon. And I'll get into that maybe later. And I've been programming on iOS since 2011. So let's create a struct. So those of you that know Swift will immediately understand what this is, but if you don't know Swift, you're going to understand later. But because I'll describe it more later and why it's important. And also, feel free to ask questions as we go through, okay? But anyways, so we're going to create a struct, which is, think of it, if you don't know Swift, think of it as C struct or a class, really a thing to hold values, right? A value object or a thing to hold a set of attributes. And the attributes this one's going to hold is identifying traits of the speaker, languages timeline, languages that I've used in anger, and then my current language of choice. And you can guess as to what that might be. So identifying traits, we already talked about a bunch of these, so I'm not going to go through it, but there they are. Languages that, oh, did I pop ahead? Yeah. So languages timeline. So one thing, by the way, you'll notice that I'm using the keyword let here. That's significant, and I'll talk about why later. But my languages timeline is basically a array, and instead of string array, basically. And here's the sort of languages from start to kind of now. So as you can see, I've dabbled and touched a bunch of languages. But started off with Apple Basic on my good old Apple II, and now I'm in Swift and the Apple world again. So that list was long. This list is shorter. These are the ones that I've used extensively, and of course in anger. Because if you use any language extensively, you have to have used it in anger at some point. And some of these a lot more angry than others. So C++ is a good example of real pissed off. But so anyway, so C++ went into Java after C++, and absolutely, quite honestly, loved it. I know it might sound surprising, but I really enjoyed that. And then, but the Java world got old after a while. Started looking for something else. Went to a language called Ruby, who some of you may have heard of, but it's kind of an improved Java, more dynamic. Got into the world of Clojure, which is very significant for this talk, and then into the world of Objective-C, which most of you are probably using day to day. So if you take that list of things that we just kind of constructed, so now my current language of choice is Swift, as I kind of alluded to, and now I'm going to set Farley Caesar as a speaker who has these attributes, these identifying traits, this language's timeline, languages used extensively, and of course in anger, and the current language of choice. Now one thing you'll find interesting is that I used a var to set Farley Caesar instead of a let. So in Swift, if you use a let to declare a, I'll say variable, but it's really to bind a name to a value, you're creating something that's immutable. So if I said that current language of choice and I tried to change that string, it would be angry, basically. It wouldn't let me do it. It wouldn't compile. But with Farley Caesar, if I change that and set it to a something else of the speaker's type, then it would say, yeah, fine, right? And so the reason this is interesting is because Farley Caesar here is a identifier for a struct, right? of this type of speaker. Whereas the let is very binding to a value. And so you can have an identity, which is the var, which is kind of a sequence of values over time. Right? Now, I'll get into sort of why that's important a little bit later on, but I just wanted to sort of set that up for you, why I constructed it that way. So, survey time. So just to get a sort of a temperature for the room, a bit of a show of hands of who here is familiar with Swift. Excellent, excellent. That's good to see. Apple would be happy to see that kind of how about functional programming? Good, good. That's very good to see as well. So in terms of functional programming, those of you that had your hands up, functional language that you used, anyone here use Haskell? Okay, good. Okay, these are the ones that are deep, okay, because Haskell is a deep, insane functional language. F#? Anyone? Okay, good, good. So that's, for those of you who don't know, that's kind of the .NET sort of functional language of choice, which is kind of like C# but better. Scala, anyone? JVM? Yeah. One or two? Okay. And then anyone Clojure? Again, one or two. Some of the same hands, so some of the same kind of looking at all the language landscape like me. So it seems like we have a good, sort of a good, cross-section of you that are, touch Swift, into Swift, and then also, looking at functional programming as a way to structure your applications, which is, I think, is a good thing. So a couple more survey questions. How many of you are grabbing one of these? In gold is the only acceptable color. I'm grabbing one, but in space gray. I'm not that crazy. So, how about one of these? In gold. Only a few? Come on. Apple Watch?
You gotta show the gold.
Oh, I see. Okay. So,
it's a sport.
Yeah, it's a sport. I get it now. Okay, okay. So maybe step up a little bit to the mid-range, yeah, you. But I think most of you are thinking, this is the one I want. So I got some rich dudes in the crowd. These are the ones buying drinks later, by the way. Because, that beautiful gold thing is starting at $10,000.
US. 13K.
Yeah, that's true. 13K Canadian.
It tops at 22.5K.
Yeah.
Canadian.
Only. Yeah, yeah.
For the rose gold.
Which is still less than a tricked out Mac Pro.
That's true. But I'd rather have that, honestly. So anyways, I wanted to just touch a little bit on Haskell. So take a second and read this. So Haskell is one of those languages we talked about as a functional language. It's kind of considered to be one of the purest of functional languages, and we'll talk about what purity means in this world a few slides on. But I'm not here to talk about Haskell. Okay, so you'll find a lot of functional programming talk a lot about Haskell. I'm not here to talk about Haskell. I'm here to talk about Swift mainly. And one of the reasons is I love this XKC cartoon because to me, like one of the benefits of a language, or one of the reasons it's important, is that the platform it runs on. And if you want to have first-class iOS apps or Mac apps, you're not going to be using Haskell, right? You're going to be using Objective-C or Swift, right? So that's why I kind of went here. So this next slide is interesting. So, those of you that have seen The Matrix, which are hopefully all of you, it's an awesome movie. The first one. So I love this quote, and I'm going to read it because I like it so much. So, you take the blue pill, the story ends. You wake up in your bed and believe whatever you want to believe. You take the red pill, you stay in Wonderland, and I show you how deep the rabbit hole goes. And I think functional programming in this sense is the red pill, right? So if you kind of buy in, right, you can get some real benefits out of going down this path. So I've talked a lot about, how awesome this stuff is, but like really what is it, right? And when you want to know what something is, where do you go? Wikipedia, fountain of all knowledge. So Wikipedia, functional programming is a programming paradigm that treats computation and evaluation of mathematical functions and avoids changing state immutable data. It's a declarative programming paradigm. I don't know. The reason I read that so fast is because at the end of the day, I don't want you to sort of look at that and try to digest that, right? I want you to think about functional programming and really what it is at its core is looking at pure functions as your base level of computation, right? So instead of in the old world that we're used to, it's objects, right? Everything's an object, everything's a class. Instantiate objects. You add your methods, you encapsulate your data. That's what it's all about. But in the functional world, the sort of level of computation you're always looking at is your atoms, the pure function. You're trying to say build up your computation in terms of functions, right? And so I just want you to take that away from what is functional programming. So if that's the what, then the why, right? Why functional? Why should I even care? Why are all these talks, coming up about functional programming? Why is there so much buzz around it, right? So one of the things that helps me remember why I'm even doing this kind of programming is this little quote. 99 little bugs in the code, 99 bugs in the code, 1 bug fixed, compile again, 100 little bugs in the code. Now I'm sure a lot of you have probably experienced this, and I know I experience it daily. And it's one of the reasons why functional programming aims to sort of help create less buggy software. And it's really because of the way you structure your application. Hopefully you have less bugs. So if you build an application or build applications where you use functional concepts and constructs, then you'll find that your code should be easier to reason about, okay, because of this notion of a pure function. It's more maintainable, should be more testable, and if you have immutable data coupled with pure functions, then you can actually more take advantage of the concurrent future that's coming for us, or it's already here actually. Because the free lunch is over, right? And every time you see that on the web, it always has different connotations, right? They're always talking about different things. But when I see this respect to programming, I think, like, where's the free lunch? Because I haven't been eating. Because it's not been free to me. It's always been hard. It's always been eating. But anyways, this is telling us the free lunch is over because Moore's law is an interesting beast where, and all of you know Moore's law, talking about the number of transistors, which should be doubling over every 18 months. And this green line kind of shows that. So the green line is showing the number of transistors. As you can see, that just keeps on going up, No end in sight. Well, there's an end in sight, but no end in sight in the near future for this one. This blue line is really the speed of our CPUs. Right? And if you look at this, yeah, it's going up. Whoa, what's happening here? We're in the plateau. Right? And this is around the year, 2002, 2003. You're starting to get this plateau happening. And you've all noticed that when you're buying your computers, that we used to be going up all the time and get to around 3 gigahertz, a little bit over, and we're stuck there, right? And the reason is because physics is starting to take over, where within CPUs, and I'm not a CPU designer, but I'm just saying that what's going on is that they're getting more and more transistors, but the speeds are sort of tapped out because of other physical reasons, where heat and what you can actually cool efficiently and all this kind of stuff, right? You want better battery life and all those engineering trade-offs happen. So this gap here is kind of interesting, where what are they doing with all these transistors, right? And you need some place to put them. Cores, that's what's happening, right? So we're getting more and more cores, right? Things are becoming more and more multi-core, and so because of that, to get the same power out of more and more transistors, you have to get into concurrent programming. And we're already touching it all the time anyway, where, and as you know, there's a lot of difficulty there, right? So, programming with multiple threads, you have to deal with locks on data. It's not fun, it's not easy, but it's something that we need to deal with. And there's some tools that help us, like, GCD and using all that kind of stuff, but it's still not that easy. I'll do a quick little aside. So those of you that know me know that when I used to talk a lot about this language when I started talking about Clojure. Why was I talking about Clojure so much? Well, when I got into it, the reason I got into it, there's something called software transactional memory, which is a concept embedded in Clojure. And it's a cool concept that helps you do concurrent programming. And so once I started, but that's why I came, but why I stayed in it was all these functional concepts that started bubbling up out of the language. And the interesting thing is that it's a nice functional language, but it's also a lift, And so that kind of said, wait a second, you take Lisp? Who's programming Lisp? So Lisp is interesting in that it really is very old, 1950s. Right? This guy John McCarthy is the guy that invented it, and I love this quote, by the way. It might be hard to read here, but it's programming. You're doing it completely wrong. Well, it's kind of mean, but the reason that actually they put that there is because Lisp was a very different way of developing it. As you probably remember, very different syntax, lots of parentheses. But the cool thing is it's actually based on functional concepts, like the embedded lambda calculus. And so it makes functional programming very easy, but it's still a very different way of doing things. But I'm going to teach you Lisp in one slide, just for fun. Right? So you look at the C function, right? Just adding two numbers, let's say. So you'll call add. You give the two parameters, 1 and 2, right? Objective-C. I mean, you could use the C, but just for fun, you're going to create an adder object, and you're going to call an add, method on it or selector. Adder add number 1 to number 2. And a Lisp, all you need to do is move this parentheses to the front, get rid of the semicolon, get rid of the comma, and you now know Lisp. Done. Go forth and go.
And I'm not listening.
It's that easy. But the funny thing is, it is kind of that easy. One thing about Lisp is actually extremely simple. Is that almost everything in Lisp is a list, and that's what Lisp stands for, a list processing language, something like that. But everything is a list, and so you basically have the function in the first part of the list, the parameters in the rest of the list, and they just kind of have as many parameters as you want. And that's really Lisp in a nutshell. I mean, there's a few other things like macros and stuff, but it's pretty much that's it. But the key thing, though, is that at the end of the day, as fun as Clojure was, and it was fun, and it still is fun, and as fun as getting into Lisp and being a bit of a Lisp weenie for a while, I realized at the end of the day, if I'm going to seriously code for iOS and the Mac, Objective-C is where I got to be, right? And I kind of started to enjoy it actually. At first, I was a bit allergic to it, but I kind of started enjoying it because I liked some of the improvements that were being made, arc and literals. I was cool with it, and I was getting really cool with it until this happened. Write the code, change the world, right? 2014 WWDC. And why was that momentous for me, anyways? Because Federighi came on stage. I'll never say his name, Federighi. Came on stage and said, "Hey, do that something new. Let the C without the C." And there was much rejoicing in the programmer world. I love this page. And the reason was because of this, right? And very cool new language that Apple foisted upon us. But some of my colleagues were not so overjoyed and kind of looked at it more like this. Swift is coming to get me, like. But I think all things considered, I think it's a good thing. It has a lot of benefits. But at the end of the day, if Swift is the new world, well, so with Swift you can say basically it's runs on top of the Objective-C runtime. It's an object-oriented language as well, so you can actually kind of one for one translate your Objective-C to Swift, right? And you're good to go. But with the there's optionals and these kind of things that are different. But for the most part, you can go for a one-to-one translation. So why functional Swift? And this quote from Chris Latner, Swift's creator, really spoke to me. And he wasn't so excited with how Federighi kind of on stage said, Objective-C without the C. And because he said that Objective-C without the C implies something subtractive, but Swift dramatically expands the design space through the introduction of generics and functional programming concepts. So Swift's creator is kind of a big believer in a functional approach as well. So I thought that was interesting and kind of led me to start thinking about it that way. So that's kind of the preamble, but what are the sort of aspects of functional that are sort of interesting, at least to start out with, right? So it's using the approach where you kind of prefer immutable data, also known as values, over mutable data. You prefer pure functions over objects, and use higher order functions where functions can be arguments to other functions, and functions can be return values from functions. So function, function, function. And Swift has first-class support for all of that. And a nice syntax as well for expressing it. And so, you know, you might say, yeah, but I can do all that in Objective-C if I really want to. I need to pass blocks around and do all that kind of stuff. But the fact is that, you know, if you remember when, for instance, C and C++ kind of took over, when C++ and Objective-C kind of took over from C as an application-level programming language, a lot of C developers were saying, yeah, but all this OO stuff, I can actually do that in C as well, right? Function pointers, you know, you can encapsulate data if you really try hard. But, you know, at the end of the day, you have to have a lot of discipline because people can trample over that, you know, that data by going underneath the scenes and touching your pointers, your pointer arithmetic and stuff like that. So at the end of the day, yes, we do that in Objective-C, but it's not about what a language makes possible, it's about what it makes idiomatic, right? So you can actually do anything in any language if you try hard enough, you have enough discipline. But if it's not idiomatic, then you're always kind of fighting against, you know, against the tide, right? So, and again, the guy that said this was the creator of Clojure, and here's another nice one, is state, you're doing it wrong. And, and he's all about sort of how you manage state in an application and without running into problems. So what's a working definition of immutable data? It's a construct whose data cannot be changed after its creation, also known as a value, right? And so that's kind of a simple definition, but I think it's a good one, where you kind of birth new values into the world and you don't change them after. And if you need a new value, you use the old value as and then you pump them into a function and you birth out other new values. And so that's kind of the methodology. But again, you know, skeptical dog says, come on, immutable data, like, how can I structure my application that way? I mean, how can I get anything done, right? And so I postulate that, you know, there are benefits to doing it this way, where since they're, you know, their values and they're persistent, they can't change out from underneath you, right? You can be sharing, you know, them around without any worry, right? They're thread safe because you can share them, right? Because they don't change. So any number of threads can touch them. They're kind of these read-only type values, and they basically take away whole classes of, you know, problems around locking and around concurrent access. So. So there's some really great talks that talk deeply about these subjects, or about this subject in terms of immutable data. There's a talk called The Value of Values by Rich Hickey. I'm going to publish these slides later this week so you guys can grab those links. And there's a really good one called Controlling Complexity in Swift or Making Friends with Value. And it's by a guy named Andy Matushak who worked at Apple and on UIKit actually. And so he's very much a proponent of functional programming, Swift, and he actually worked with Swift before, which was at least one of the very few within Apple. So he has some really good talks on this stuff. So in Swift, there's sort of value types, which are numbers, strings, arrays, dictionary, enums, tuples, structs, and reference types, which are basic classes. So you can see how Swift is very much weighted towards this value-oriented approach, right? And which I think is interesting. But so what is a value type in Swift? So it's kind of this atomic thing, right, where it's copied on assignment, it has a single owner, okay? And what do I mean by copied on assignment? So I took this from an Andy Matushak slide. But what it means is that all of these types kind of act in this way, where, and this is an example with an integer. So if you have A, which is a variable that has the value 10, you have B, which is basically the same value as A, right? So A and B now have 10. If you change B to 5, then A will have 10 and B will have 5, right? So that sounds, you know, that makes sense, right? That sounds pretty simple. But that's actually quite different from a lot of the work we do in Objective-C, where everything's a pointer, right? And if you kind of do this type of work, you'll find that, you know, you're referencing the same thing, so one thing can change another. Right? And that's the idea of a reference type, where there's multiple owners and it's shared on assignment. Okay? And what does that mean? So if you look at that, if you have now an object, right? So reference type in Swift class is a good example. If A is a UI view, right? B is now pointing to, or has the value that A has. That value is actually a reference to what A is referencing, right? So it's a pointer. And so if you look at the alpha value of A and alpha value of B, they're the same. But if I change the alpha value of B, then the alpha value of A is now also changed, right? And so because it's a reference type and you're sharing, that same object, one can change the other. And so, as all of you have probably found, all kinds of little bugs can fall out from this, especially when you're sharing amongst threads and stuff. But even in a single-threaded application, if the code's far away from each other, you get this kind of action at distance situation, which is tends to be not good. So how do you defeat this? Pure functions is one of the aspects of functional programming that helps deal with this issue. So what's a pure function, right? What's purity mean? That's another one of these long-winded explanations from Wikipedia. But the key thing to take away from this is a pure function is a function that takes input, churns on it, and gives you output. And the function is only dependent upon its input. It doesn't touch anything outside of itself to sort of give you that output. And that's really what a pure function is. And one thing that's really interesting too is that a pure function also has no observable effect outside of its input. So it can't sort of print to the standard console, it can't access the database, right? And it can't mutate its input as well, it can't touch it to change its input, right? So that's a pure function. So you can see there's a lot of restrictions there. But those restrictions give you some power, right? In terms of being very certain about what a function does. Because with a lot of our development, if you look at a function and it takes some input, you can't be sure that it didn't change that input while it was doing something else, right? Unless you're very disciplined. So in the abstract, a pure function, y equals f of x. If you look at square root, right, it's a pure function. It's a pure mathematical function. And for any given value of y, it'll produce some value, any given value of x, it'll produce some value of y. And for each x, it'll always be the same y, always. Doesn't matter how often you do it, when it's run, right? It's always the case. So in Swift, I call the square root of 16, I'll always get 4. Doesn't matter when I do this, how often I do it, right? And that's a lot of power in getting this function that always does the same thing. Functions also give you referential transparency. So this is one of those terms always thrown around in functional programming. What does it mean? All it means is that if I have a function y equals f of x, right, it's pure, that means that if you have f of x, you can always substitute it for the y, right? They're basically the same thing. So if you have the square root of 16 and equals 4, you can always substitute the square root of 16 for 4. Right? And why that's really cool is that as you're developing these pure functions, even when you're not done developing one, right? If you know what input gives a certain output, you can kind of put aside the development of that. Like just say I was developing the square root from scratch, right? I know this square root of 16 should be 4. So in my testing of that function, if it's not done yet, I can still take that 4 that I know, give an input of 16, and then use that 4 in the rest of the program. And then once the square root is done, it will just work, right? And it seems simple, but it's really a powerful concept. Okay, so for those of you that aren't familiar with Swift, this syntax for a function is pretty simple, right? Whereas you have a func keyword, the name, right? It's parameters, and so x of type int returns something of type int. Usually that's not in brackets, but you can put it in if you want. And then you have the curly braces and then the body, right? No semicolons. So it's pretty simple. And then use is just the calling is very much like a C-style calling. And Swift has something that are called closures, which you basically have this concept of a closure is something that is like an anonymous function, or not anonymous, or a freeform function that it has an input, has an output. It can also close around its state as well, right? The state of the program around it. You can actually capture those values. And with Swift, basically you can define a closure like this, which is here's the name of the closure. It takes int as an input, returns int as an output, and then here's the value of the closure, right? So that's one way to declare it. Functions are also named closures in Swift, so they're almost equivalent. You kind of use them in place of each other. So as I said, with closures though, they capture their surrounding scope, so they're not pure. And so they're powerful and useful, and you use them all the time. For instance, when you're when you're using your NS URL session, right? You have a pass and callback, this kind of thing, right? Like it's good to these are good things to have, but it's good to know that they are impure and they capture their enclosing scope. So that's why you get this problem, for instance, of capturing self. If you use a closure, you know, what it's enclosed in, it captures self, and then you can have this kind of circular reference if you're not careful. Right? So they're not pure, but they are useful. But the interesting thing about closures is the fact that you can actually just use them as I said, how can I put it? You can pass them around and you can return them, right? So here's an interesting example where you have this let x equals 5, right? And you have this function called add 5, right? It takes an int, returns an int, and returns x plus 5. So you notice that x was not defined within this function, it's defined out here. So it actually captures that 5. So if I call add 5 and give it 50, I'll get 55. Right? So it actually captures that. And the cool thing about them actually is kind of neat. It captures that forever, for the lifetime of that thing. So that if I actually take this function, add 5, and store it, right, in a dictionary, right? So this is the Swift dictionary syntax. You have a function dictionary, maps a string onto a closure, and the closure takes an int and returns an int. And I can say, here's my string key, here's my value, which is add 5, which is actually the name of that function. And if I use it later on, right? So what did I do here? I said, I retrieved it out of the dictionary, right? And then I just called it on 50, and I get 55, right? And I can even use the dictionary syntax to call it. So the interesting thing to know is that this is very impure, but it's quite powerful. You can use it in interesting ways, but you have to know what you're doing. So yeah, so as I talked about, you can have functions as arguments. Now, I showed you kind of the impure way to use them as arguments. There's and this is an example from a real, quote unquote, real application using EventKit, right? I don't want to go too much into this, but that's just showing sort of the way that we kind of use them commonly. But the way we really want to, and I'll talk about a little bit later how to use them purely in a few higher order functions. But this is how you use them as a return value. And so, again, and this is a little bit unintuitive, we've never done it before, but I'm going to create a greater than function, right, for a particular number. Okay? So I'm actually going to create a function that creates a function. Okay? And so greater than function takes an int, returns a function that takes an int and returns a boolean. Okay? So this is, again, a very interesting thing with functional programming you can do where you can actually return a function. So I said, let my greater than function be a function that takes an int, it returns a boolean, and then this is the closure syntax that hopefully some of you are familiar with. So this is the sort of input parameter, and I'm going to return if that input parameter is greater than n. Okay, and n is the outside the scope here, right? And then I'm going to return that function. So that's kind of confusing, but if you haven't seen it, here's how I use it. I'll say let is greater than 10 equal greater than function for 10, right? And then I can say is greater than 10 20 true, is greater than 10 5 false. Right? So it captured that value, and now I have a function that I can use with that value kind of stuck in it. And so some functional programmers use this kind of technique to almost create this notion of objects, but they're pure, where you can give them some state, and then you can use them later on, right? But they can't be changed. So, but to be honest with you, I don't use the returning as a function very often. I use functions as arguments, but not really as a return value very often in practice. But just interesting to know you can do it. Here's another nice quote, right, to think about, where the future is a function of the past and doesn't change it. Okay, what does that mean? Right? So that means that any future values of your program should be a function of past values. So you take your values that you have in the past, you pass them into a function, you get future values. And this is how you kind of move forward in time. Right? But you don't want to just change things in place, because that's where errors come. Okay, so what are your go-to sort of functions in sort of an introductory sense in functional programming? The three you'll always hear about are map, reduce, and filter. And these are kind of your go-to functions. And these concepts have actually been built upon, in a lot of big data type applications, right, not produced, to sort of do very quick churning through data. So it's actually can be used in the small and the large. Okay, but what does map mean, right? So you probably heard, this kind of idea of map and functional programming. Basically, it's taking a, let's say, a collection of data, having a transformation function, and then coming up with a new sort of collection, right? And the new collection has the data transformed in some way. Okay? And by the way, this graphic was produced with an app called MonoDraw, which was just released. It's kind of a neat app where you can actually build text diagrams, right? So that's actually text that I just cut and paste out of the app and put it in here. Right? You can actually put it in emails and all that stuff. So it's kind of neat for if you're using Markdown and that kind of thing. It's really cool. So this is kind of how map is declared. I don't know if I want to get into this too much. I'm going to go on a little bit. So getting into generics, and that's a little bit more on the advanced side of it. So let's give a quick example of map, right? So let's say we have a requirement that says produce a list of the squares of the first 10 positive numbers, right? So we're saying take the first 10 positive numbers and square them and give me what that list is, okay? So there's the imperative approach that most of us would do, which is I'm going to create my first 10 positive integers. I'm going to create an integer array instantiated, and that's going to be my sort of holder for the answer. And I'm going to loop through those positive integers, and then keep adding the answer right to my integer array. And then I can print it, and then hopefully I should get the right number or right answer, which is at the bottom here. Right? So this is perfectly good, but a functionalist would look at this and scoff, not like it. Why? Why would they not like it? Well, it kind of mixes the mechanism with the policy. What does that mean? So the mechanism to solve the problem is sort of looping through the array, right? And the policy of what you want to do with each item is kind of embedded in that loop, okay? And also, it's not very declarative, so you have to kind of work through those steps to see what it's doing. It's not kind of telling you what it's doing. And the other part of it is that it can lie to you after the fact. So once you've done it, you have this hanging around, this first 10 squares. Remember I named it, so I named it first 10 squares, right? So at the end, you have first 10 squares as a named variable that has the answer in it. But I can fool around with it, and I'll just append a 23 to it. Why not? And then print it, and now it's telling me first 10 squares is equal to this, the 23 at the end. Well, that's wrong, right? So I should change the name of it if I want to start adding to it. Or I need to take first 10 squares and make that immutable, so then no one can change it, so now it makes sense, right? And Objective-C land, I would do this a lot, where I'd be creating some structure, and then sort of say like an immutable array, and then I would return an NS array to make sure no one can change it later, right? So it still makes sense after the fact. In functional programming, you don't have to do that, right? So the functional approach is much simpler. You can see there's much less lines of code here. Because the cool thing is that really what I want to do is take the first 10 positive integers, right? And I want to square them, right? And for the answer. And so remember that picture I showed you. So this map function takes a collection, right? Transforms it and gives you a new collection. So this gives me actually a new immutable collection called first 10 squares. Okay? Now, hopefully you're kind of familiar with this syntax, but what it's really doing is that this is a method on array, and it takes a closure, and the closure takes an int and returns an int. So you kind of put it, since it's the last thing in the argument list, you can kind of put it at the end. And also, if you want to have a short form, you can actually call the arguments $0, and if it's a second argument, $1, third argument, $2. You'll get used to that after a while, but there's also other ways of structuring this, which I showed you. So you might find this more readable, where you can actually create a named closure or a function called squareInt, which takes an int, returns an int, returns the multiplication of those, right? Then you can pass it into map. So first 10 positive integers dot map squareInt, and then it'll return your first 10 squares and get the same answer. Right? So there's many ways of structuring this in Swift. Depending on your use case, you will do it one way or the other. And there's even other ways where you can do that whole number in syntax. And then so you can say, first 10 squares, sort of first 10 positive integers dot map. Here's my closure. Number is the parameter, return number times number. And so however you want, like it's just whatever you find most readable. But what are the benefits of doing it that functional way instead of the imperative way? It's more declarative. It states exactly what we want to do, not how we want to do it. Right? I want to map this set of values to this other set of values. Right? So think of map as transform. So it separates that mechanism now. So I'm not stepping through anything anymore. It's calling a method called map. And the policy is what I plug in terms of that closure. And it's encapsulated very nicely in that closure. So I can always take that policy now, and I can kind of pass it around. I can change it, and not have to go through and change my looping or anything like that. And here's kind of a numerical way of looking at what we just did. And now, if I try that little fun thing I did before, which is now take my first 10 squared and say 1023, not going to be able to do it. Right? You can get an error because that thing we got out is immutable, right? So what we passed in was immutable, we got out was immutable, and that's the beauty of sort of functional coding. Right? So I talked about map. Here's filter. Okay, it's another one of the key things you're going to use in your functional toolbox. Filter is again very similar, right? You take an initial collection, you're going to transform it to a different collection. Okay? This one's a little bit, so it's not the exact same size. You're trying to filter things out of it, basically, right? That's why these boxes are the same. And here's the declaration, not that important. So how are we going to use it in practice? So let's take that requirement and add a little bit to it. And let's produce a list of even squares of the first 10 positive numbers. Okay? So how we do it in the imperative world, again with another loop, so I'm not going to go through it, but you create your initial item, you create your answer holder, you loop through, you have some logic to decide what to put in the answer, and then you spit out the answer, right? And here the answer is 4, 16, 36, 64, and 100. So these are the even squares between the first 10 numbers. Functional approach, as you can see, a lot less code again, and all we did was we did the map thing we did before, right, to get the first 10 squares, and then we said filter, and anything that's divisible by 2, right, so this mod 2 equals 0, anything divisible by 2, filter that out, right, filter that in, I should say, and then filter it in, then you'll keep those in the answer, you'll get this. So again, all lets, by the way, right? No bars, right? So this is very quote-unquote safe code. Last but not least, reduce. Okay? So reduce is, again, this is kind of the shape of it. It's interesting where you take, again, a collection, and you want to transform it and come out with one little thing at the end, right? So what's the most common form of reduce? Probably summing something, right? So let's say, what is the sum of the even squares in the first 10 positive numbers? You can tell it's a pretty made-up requirement. Anyways, serves our purpose. So again, the imperative approach, a lot of code you loop through, you do all the logic we talked about before, and then you kind of filter out the ones you want to add into the sum, right? You add it here, right, and then spit it out there. Okay? So again, it's relatively simple, but as you get more complex, loops, I know all of you probably had the case where you're dealing with loops that are, you're trying to debug to the end of time, right? Whereas the functional approach says, well, reduce is just again an operation that, so you map against it, right, to transform it to the squares, you filter it to keep in the evens, and then you say reduce, and this is a little bit of interesting structure, but what it says is that I'm going to reduce this thing, right? And the policy for reduction is start with the value of 0, okay? And then combine it by taking the first thing you get and add it to the next thing. And keep doing that until you're done. And so reduce, sometimes you'll hear people, functionalists, talk about left fold, right? Reduce is the exact same thing. you're actually taking an array or a collection of things, and you're taking the first thing, right, and then the second thing, adding them together, and moving along, adding that to the next thing, moving along, adding to the next thing, moving along, right, until you've summed it all up, and it spits out the number. Right? But all that mechanism, again, is taken care of for you, which is awesome. Right? And again, all immutable, which is cool. Oops. So one thing I want to say is that I was showing you everything about arrays, right? But the interesting thing with Swift, and this is the part that I haven't dived in too deeply, but Swift has something called the sequence protocol. And it's actually very similar to something in Clojure, where they have the sequence protocol as well. And what it means is that all of these functions, these functional sort of map, reduce, filter, and there's a bunch of others that I haven't touched, they don't just work on arrays, they work on a protocol called sequences. So anything that kind of has a value, it can take and generate a next value, is a sequence. And all these Swift data types actually conform to that protocol. And so the cool thing is that so not just array, but string conforms to that sequence protocol, range does, dictionary does, and there's others. And why this is cool is that you can actually look at a range, and if you know Swift, you know that a range is kind of declared this way in terms of syntax, right? So this is a range from 1 to 3, so 1, 2, and 3, right? And I can say, and the other thing too is that they put in some convenience methods on array, where you say array.map. But map is actually a kind of a global function in Swift. You can pass any sequence into it. So you can have a map and put an array into it as well, like the other way around. And so this is saying map, put a range into it, and then here's my policy, make each one of those times 2. So then you get 2, 4, 6 at the end, right? So the cool thing is now you're using those same map, reduce, filter, on and on against ranges now, right? So you're getting this kind of multiplying effect of, I know exactly what this function does, and I can do it against all kinds of different data types. And interestingly enough, strings are sequences as well, and they're just sequences of characters. Okay? And so I don't want to go too much into this because it's starting to get long now, but this is really looking at a string, and I really want to replace all of the character O with underscore, and I'll pass in some value, right? And so the key interesting thing about this is that I'm doing a map again, right? Taking in the passage and doing the transformation, okay? And this is really just looking at the characters in that sequence, transforming them to underscore if they meet my criteria, right? Actually, I've hard-coded here. That should be the replacement thing. But anyways, not important. And then you get this out. But the key thing about this that I'm trying to show is that I'm using the exact same technique, map, right, against the string now, right? So you can process all kinds of things, using these kind of basic techniques. And the cool thing is, like any protocol, you can implement your own sequence protocol as well, right? So you can create types that actually implement the sequence protocol. And if you do that, then all of the things that operate against sequence protocol within Swift, you get those for free. So I could see, sort of streams of data, for instance, could be something that you could implement sequence protocol and use map and reduce and filter against them, stuff like that. It would be cool. So as you can probably tell, I love this pattern, right? You have a mechanism, and you have a pluggable policy, right? And one of the things that a developer I worked with a long time ago said, one of the best things you can do in programming is separate mechanism from policy. You put them together, right? Your programs become very intertwined, spaghetti type, stuff. But when you separate them, then you get a lot of power, right? And that's exactly what the Swift designers did. And I love it so much that there's an example in Ruby that I really like where you can take a collection and call .each on it, right? And then they have a very little bit different syntax, but this is the sort of input variable. So for each item, inputs is like their print line or NSLog, the item, right? And you get this kind of thing in Ruby. And Ruby also has a each with index as well, which is a similar thing where you get the index and the item as well. So I said, what the hell? I'm going to implement this in Swift. And it was really easy, which is you just send an array, did a do for each, right? And then take an enclosure, that's your policy, and loop through the indices, right? And then call the closure on the item. And do for each is the same thing. And they work exactly the same way. But the cool thing is that these ones are not truly functional because they have side effects, right? You're doing a print lane, right? So you're just doing something against each value. So you're not mapping, you just want to do something with it. But it's, it's a little bit nicer than running a loop against it, right? And again, any sequence you could add this to. I just did extension for array for my purposes, but any sequence you could add that against. And that's the Swift version. All right, so we're coming near the end a little bit. So, these are nice core techniques to use when you're developing, but how do they fit into my application architecture, right? It's fun using little toy examples, looping through arrays of numbers and that kind of thing. But where can I really get some benefit here? And the thing is that at the end of the day, I'm not going to mince words. COCO and COTEX are inherently imperative environments, right? They're based on OO and imperative techniques, right? And so you don't get any benefit from fighting the framework, okay? And so I'm not going to pitch that. Now there are people that want to fight that framework, and I might say something controversial here, but the reactive COCO guys are kind of trying to do that, and I'm glad they're trying to do it, and I'll talk a little bit about that in a second. But at the end of the day, if that shell is really inherently imperative, you can't control it, so control what you can control. So there's a guy named Gary Bernhardt who is in the Ruby world, and he proposed this kind of structure. He calls it functional core imperative shell. And I think that's a really, really cool concept. And really all it's about is the core of your application, right? You try to be as purely functional as you can be with it. It makes it very easy to test, easy to reason about, easy to work with. And then as you get out to the shell, which is talking to the UI, talking to the database, talking to the file system, you're dealing with that imperative framework. So you kind of take your core concepts and you kind of work with the framework with them, right? And this is really what this is saying, right? And the key thing with this one is actually, I kind of missed the. There's a great talk on this from a COCO perspective called Enemy of the State. And this guy that I guess Rob Riggs works with, Justin Spar Summers from GitHub, did this talk, and it's really good. But really what you're doing is, and Andy Matusak talks about this, you're kind of playing a game with yourself where you're trying your best to make as much of your application as purely functional as possible, right? So this kind of nice, pure world that just works nicely. And then as you get out to the edges, that's where you have this kind of area where you're dealing with that imperative outside world. And you basically, as you push your state out to the edges, you just can represent that state as objects with mutable references to immutable core constructs, right? So your constructs in the core are immutable. On the outside, you're mutating the outside world. So mutating a label, for instance, to have a new value, UI label a new value when you change something. And the benefits of this is that really nice side effects, right? So testing the functional pieces is quite easy, right? Pure functions, really easy to test. It also allows sort of nicely isolated testing, right? And you have an imperative shell now that has relatively few conditionals, and it makes reasoning about the program state over time easy. Okay, so I didn't talk about some of these advanced things that you'll hear in functional talks, like laziness, which I like, flat map, currying, functors, applicative. I said I wasn't going to swear. Sorry. Monads. So all of these things that you'll hear a lot in functional talks, they're a little bit on the advanced side, and I don't think you don't need to start with them to get goodness from functional programming, right? And sometimes a lot of talks will start with this, and then we'll lose everything. So as I learn more about them, I hope to let all you know about that. But there's really good resources to sort of, if you want to go deeper into this world, right? There's a great functional programming in Swift book. It's out by the opc.io guys. It gets pretty deep pretty fast though, so take it slow, read it a couple times kind of thing. But it has some good stuff in it. This whole thing about a monad is a very difficult concept to explain, and you'll find all kinds of things on the web trying to explain this concept and doing it really poorly. But there's this lady, I forget her name, but she did a great talk on InfoQ about why a monad is like a writing desk. and it really explains the concept really well. Right? You have to get it. And then there's a good book called, and also free online book called Learn UI Haskell for Great Good, if you want to go into that Haskell. Okay, so we're coming to the end now. So we talked about, the core, right? We talked about that imperative shell, and there's sort of a final frontier of functional programming, which is the UI, right? And it's like, can we make this functional? Like, can it be done? So there's a great quote by Josh Abernathy who says, right now we write UIs by poking at them, manually mutating their properties when something changes, adding and removing views. This is fragile and error prone. Some tools exist to lessen the pain, but they can only go so far. UIs are big, messy, mutable, stateful bags of sadness. I love that. And I think it's true, but we deal with it. And what if we could make the UI functional? I mean, it would be the holy grail of UI, because now if you have sort of values coming in, right, immutable values, a function turns on it, and you have a value of the UI come out, right, then that makes that UI really easily unit testable. Okay. Also, you can have another benefit is arbitrarily large numbers of undo, right? Because if you have this value, right, you can actually just say, I'll keep track of the old values, right, and just keep popping them off the stack, right? It becomes very simple. But this is something that a lot of people are churning away on, trying to figure out, and it's really not quite there yet, quite honestly, right? But I think it's an interesting space to watch. And the React to Cocoa guys are trying their attempt at it. I don't like that one as much as there's something called React Native, which Facebook came out with. Don't like the fact that it's in JavaScript, but it is something that's achieving to look at this area and take an approach. And one of the guys from the functional Swift book is writing some work on what he calls functional view controllers. And exactly what I just said, where you have some value come in to a view controller, and you have a view controller come out the other end. It's changed because of that value. It's immutable. It can't be changed. So I just really skimmed the surface of functional programming and functional programming in Swift, but it's definitely a fast-evolving area. And you're really taking very old techniques. Remember I showed that guy, John McCarthy, 1958, right? Those are old techniques and really Lambda calculus comes from the 1920s. But because of some of the interesting things of the modern platforms we have now, and our ability to program concurrently and program in this functional way, kind of brings these techniques forward to now and why they're kind of relevant now. So all I can say is that if you're just starting out, ease your way into the topic. So if you see any of these functional talks that jump right into that, talking about monads and stuff like that, flip the switch, turn it off. Kind of slowly level up, because once you start to level up, everything starts to sink in, right? Like anything. But let's not call it something what it's not, right? Swift is not a purely functional language, right? It's a hybrid of OO and functional. And because of that, some treat it like Haskell and try to do very advanced things in it, but it starts to fall down, right? It just doesn't have that kind of support. But it does have enough support where you can use functional techniques to make your programs better. And remember the red pill. The rabbit hole of functional goes down pretty far. And by the way, I know it's not a red pill, it's red and orange, or red and yellow, but emoji is what it is. Another great talk to point you to, Andy Matushak. It's called it's called Functioning as a Functionalist. And he just kind of says about separating the, kind of ivory tower stuff from the practice. So just check out the resources I mentioned in the earlier slides. There's a Functional Swift conference that happened over the summer, which has some interesting talks. And if you have time, and I know most of you don't, but if you do have a little bit of time, poke your head outside the iOS world or Mac world for a little bit and check out some of these functional languages, because they really change the way you think. I think it does improve your development in our world. So if you remember nothing else, though, from this talk, right? Remember the preferred values over references when you can in your development, okay? Value types over reference types. Prefer pure functions over impure functions and procedures. So again, when you can use them, but sometimes you can't. and reach for map, reduce, and filter over 4 when you can. And there's sometimes where you'll see this is a for loop, standard thing I'm doing, and you'll think, okay, Farley said look for map, reduce, and filter, so I'm going to try that. And you'll see, well, I don't know how to quite apply it, but if you think a little bit, it'll come. And when it comes, it's kind of like a revelation. Right? So my contention is that the future is functional, and thank you. Okay, I know it was a bit of a long talk. I hope I didn't put you all asleep. Any questions or comments? If not,
Are you going to be sharing these slides?
absolutely. So I'm going to do a comb through just to make sure. Mostly pictures I got from the site called City, which has sort of these public domain pictures. So most of them I got from that. There's a few that you get. Just got to make sure about the attribution on that, and then I'm going to publish a couple days. And so I'll let the whole group know.
Yeah, broadcast some of the
So,
well, do you know any real-world stick projects that use functional?
yeah, actually, the guy that you mentioned,
Garden Fund.
Yeah, Gordon Fondo. Yeah, he actually has a GitHub repository. A lot of real-world stuff is using functional concepts, and it's some pretty deep stuff, but it's a great place to start.
One project you might have heard of is something called Argo. It is because parsing JSON in Swift is fraught with peril. So they wrote this framework to parse JSON in a functional way, and it's called Argo, and it's open source in their GitHub project. So and it's actually fairly readable if you want a good introduction to what you can and can't do and this kind of thing. But really, all the stuff that they're doing are things with their podcast. They start about Haskell and monads, and actually in his talk title, I told him don't put functor or monad, and he ended up putting functor and monad. He said it was a better title. But, so don't run. But it should be very, very good. So,
Absolutely. Yeah, that's a great place to start. And those guys, you know what they're talking about. And the functional Swift book, I think they have a lot of, if you go to opci.io, they post a lot of sort of topics from their book on the site, and look at a lot of code. So that's a good place to be.
there's another thing about Thoughtbot. They just published a book called Maybe Haskell. So if you're not sure about Haskell, maybe Haskell would be a book to look at because it's, for a point of view of functional programming, somebody who's kind of programming.
Yes, great talk, Mark. Awesome. One of the things that you're talking about is a way to make interface functional, and it's a big challenge. One of the things that I've heard about is using a different design pattern, the long view model design pattern. Do you see that as relevant in the way to use functional programming on a UI side?
Yeah, it is, and I've dabbled like a little bit with it, and for those of you that probably heard of it, if you don't know what it really is, it's kind of a way of like looking at your views and how you have a domain model, right, for your domain logic. It's having sort of a pure view model, a plain old Objective-C object or Swift object as your view model, and then you have your view read that to render, right? So you have a bunch of view models for all your views, right? And I think that it's not inherently functional, but it can be, right? If those view models are immutable, okay, and pure values, then if your view models actually represent your view, right? Because the view is just a rendering of that. So a UI label is just looking at a view model and rendering it based on the data in there. But if that data is immutable, then that's the thing you can test. Right? So it definitely approaches that world of making it functional. That's a good point.
I got a dumb question.
There's no doubt.
People, when they talk about functional programming language, they always talk about a pure language. The functions would never have any side effect. And that printing would be a side effect.
Absolutely.
Well, how the hell does a purely functional program ever accomplish anything?
Yes.
It's not allowed to print a result.
Yeah, because if you can't print a result, all you're doing is warming up the box, right? But I'm going to...
Is heat a side effect?
And heat is a side effect.
Acceptable side effect?
Thermodynamics.
Exactly. But I'm just going to show you something real quick, which is one of these guys. So if you look at the functional one, okay. So if you think of this as your immutable core, right, or your functional core, your imperative shell, you kind of get that sense of that application architecture. So you're right. You can't have a purely functional program. It is impossible. But I'll tell you what Haskell does to try to achieve that. But you can't have it. But what you can do is functionalize most of what you have, right? So this all is purely functional, no side effects at all, right? But at the end, I gotta have a side effect of like seeing what happened, right? And so so you try to isolate this, right? Instead of having this throughout, you try to isolate it in a very well understood shell, so to speak. And Haskell is the purest functional language that I know of. Don't know, but know of. But it tries to like create this monadic input-output structure that you kind of write into, and then it renders in some way. It's a little bit funky, but either way, that's.
So the challenge where I see that this becomes more interesting is when your functional world gets a little more complicated, and somewhere along the line you don't get out what you're expecting, right? And it's that, how do I open that up?
Yeah.
Right? And an old-fashioned way to do it is put in a lot of print statements.
Yes.
Right? And I know it's all grody, right?
Yes.
Right? Sure. And
That's a good point.
and there wasn't a discussion about breaking this up in units.
That's a really good
break it up. Sure.
Yeah, no, that's a very good point where, if I don't have any print statements here, like if I did something weird here, and I get a weird answer here, like where do I, throw in my, so again, the debugger can help where you stepping through. But what I would do in that case is, this is kind of a short form for slides, but I would kind of try to have named functions here, right? And then test those named functions, right? And then, if you're sure they work, right, then you can start to combine. But you're right, and sometimes in the combining of them, you might combine them wrong. Then it's hard, but that's one of the, nothing's perfect, right? So it's one of the trade-offs of functional things.
Just getting back to a question here about UI and how that can be made functional with MVVM. Does React solve that a little bit? Like React pattern or flux pattern or whatever it is?
Yeah, so React is interesting, and I kind of brushed over it, and I'm no expert in it. But what I understand about React from Facebook is what they did was they took the DOM, right, in the JavaScript web browser world, and usually what you do is you kind of poke at the DOM to change the UI, but that's inherently slow, right? So they have this idea of a virtual DOM, right? So it's an in-memory kind of construct, and they change that thing as the program changes. They need to change the UI, and then what they do is they do a diff against the real DOM, and they only change the things that on the real DOM that actually change, right? Which is kind of a neat thing, right? And they're trying to bring that notion to the native world. And I'm not quite sure how they're doing it. I haven't looked at the React Native too much, but it's kind of an interesting concept, right? And it's kind of, again, it's all around, everyone's fluttering around the same conceptual, basis and trying to do it a little differently. So that's kind of interesting.
I did watch the talk on that. It's hard to watch because it's really politically biased.
Right, yeah.
Two big things. It did a lot of code generation.
Yeah.
The other thing was all the layout was done in a JavaScript one layout library, so it was all done fixed.
Yeah.
And we didn't work with auto layout or anything like that. So you know how big your screen is. It all goes into the JavaScript. The library calculates all the recs and comes back.
Yeah, I think at the end of the day that React Native as it stands today is a cool proof of concept, and for the reasons you talked about. Right? One, the JavaScript's no thanks, but the other part is the fact that you said like it's not looking at sort of an auto layout and looking at adaptive UI and this kind of thing. It's not that advanced. So I think it's more of a cool proof of concept that they did it, and there's neat things they show in the demonstration of it, by the way, where when we change something and want to look at the UI change that we made, we have to recompile and run again, change the color or anything like that. Whereas they were just changing these things on the fly.
Yeah, that was kind of BS. If you wanted to build that for local, you could make a server, you could download all your parameters.
That's true.
That's all it was doing.
That's true. But either way, it looked interesting. But I think it's a
As you start using functional